Okay, so today we will start the second lecture, introduce our first payroll programming language called MPI. And as you can see from its name, it's a programming language based on message passing communication method. So it's one of the methods we introduced before for supporting communication between processes. So that's why this is the language or the programming library developed based on that programming model. So we will have a brief introduction of the history of MPI. And then before we talk about the API for MPI, we would like to briefly introduce or clarify some of the communication methods so that it will help you to understand the behavior of those API code. And then you can see MPI doesn't have that many API. The design of the interface is supposed to be as simple, as efficient as possible. Roughly, all those API can be classified to those three categories for point-to-point communication, collective communication, and some management routine. And finally is the I/O API from MPI. As we mentioned, these are the set of API for payroll I/O, or payroll operation on a single file. Right? So what is MPI? It's a short name for message passing interface, right? So you can see it is based on message passing programming model, and it is only an interface. Okay, so as we all know, the purpose of the interface is to provide portability, right, and the programmability. So it's only a specification for some methods, right? And so actually, there could be many implementation of the interface. That's what we call the library itself. Okay, so but as a programmer, right, when we do the programming, we only care about the specification of the interface, not the implementation of the interface. So that means we don't need to worry about how those interface or API could be implemented efficiently on your machine. Or that also translates to you can choose which library you use to compile with your MPI code and to run on a certain machine. So the beauty of the interface is that the programmer doesn't need to know or need to care about the detail of those implementation, right? And on the other hand, the efficiency of the interface can be optimized or designed or controlled by the MPI developer. Those are usually the person that familiar with the systems. And as we introduced in the for a supercomputer system, right, there are a lot of ways they need to be could be used to optimize the performance, and some of them require customization or modification to the communication protocol or the library, such as MPI library. So the MPI developer or the supercomputer owner or manager, they can optimize the performance for their specific system without worry, how would that affect the user. Okay, so that's why interface is important, right? You can separate the concern and allow the programmer and the system developer to solve their own problem. Okay. So of course, there are many MPI library such as MPeach, MRPeach, Intel version MPI library, etc. So depends on which machine or what type of system you are running, then you can choose the best library to use. Right, and another example is we also talk about some new communication interconnects like the infinite band, right? So again, infinite band has its own driver. It has its own way to implement the network stack. So of course, you will also have some MPI library that is specifically designed and implemented for infinite band. So you can see depends on what's the underlying hardware or system you choose. Sometimes you have to use a different MPI library to maximize the performance as well. Okay? And for this course, of course, you don't need to worry about that. Our cluster or your programming environment has been all set up, so you don't need to worry about which MPI library to use or how to install it. Okay? But of course, if you build your own parallel cluster, then you probably want to test and install those MPI libraries on your own. Okay. And the reason, right, the MPI choose the message passing programming model is because, as we introduced, this is the programming model that is more suitable for distributed or large-scale parallel computation across machines, right? So MPI is actually a very old programming library, but still widely used today when you want to implement a parallel program across large-scale machine or distributed systems. Okay. And so, as we mentioned, the benefit of having this interface, you have portability, and the benefit of message passing model is you have scalability. And as we mentioned, MPI is an interface that can separate the control, so provide the flexibility for the developer and the programmer. Okay, so it's not MPI is not perfect, but it's definitely sufficient and easy to learn for writing a parallel program. So here is just a short introduction of the history. So where the MPI comes from, right? So before we have MPI, you can imagine we already have those parallel computer systems, or people already try to solve their problem on multiple machines. And of course, they run into all those problems for running a parallel program, right? For example, they need a way to communicate the processes across machine, and and also they need to manage those processes and need to figure out how to handle the memory management, etc. And so at that time, everyone just like a new topic, a hot topic, right? There's no standard. So everyone try to solve the problem they encounter in the best way to their application and the computer system they use. So there are all kinds of solutions. And the problem is that there's no compatibility, or there's no collaboration between those solutions. So as a programmer, sometimes will be hard to integrate them together. And so there's no way for them to write. And if you write a program using one solution, and you're not able to install that on another machine, then you cannot run your code. So that causes lots of issues. Okay? So people start to sit down, right? You have the forum. That's always what happens for software, right? That's why we have those, 5G forum or other forums to discuss the spec and the standard for some technology, right? And MPI exactly the same process. So people start to sit down together, discuss, and try to have agreement on what's the API, what's the interface for parallel programming should looks like, and hopefully that can cover most of the library, the technique we have, and right provide that as a unified solution to the programmer. So that's how we have this interface specifications. And the MPI is not actually quite basic. We don't want to make it too complicated, so it doesn't change too often. And as you can see, right now, I think we are only at the stage of MPI 3 something. The change from MPI to MPI 2 is the MPI IO we will introduce, and of course, go with along some of other um, unique features or new API. But the change not that large, except MPIO is definitely a huge important change to the interface. Okay. All right. So as I mentioned, right, the timeline of this development is that start with those incompatible software tools that get developed, and people see the need, see the potential, but they also think it's already at the point we need to have some standards so we can make the development even faster, right? And we can focus on the application, the problem, not a portability or compatibility issue. Okay, so that's why we have this standards get discussed and finally get decided by the MPI forum. And you can see the participants of the forum comes from all sources, right, including individual developer or the computer vendor who decide the hardware architecture, and academic because they have some research, right, and they have some techniques, right, and also the scientist, because we said at the beginning and today still mostly the people use parallel programming is those scientists, because that's how they implement their scientific application. Okay, so all the people that involve parallel programming in one way or another, they contribute to this forum, and of course at the end they make a draft and finally announce it in the supercomputer conference. So this conference, particularly, you should know if you want to get to know the high performance computing community. This is the most important conference because the founder, right, is the leader for this community, and so many important things and announcements are made in this conference. And this conference is unlike normal conference that only just present the academic research result. This conference is supported by the vendor, the industry as well. So this conference usually they are hosted along with another a show from the industry to announce their latest, for example, GPU model, infinite band technology, etc. So this is a very, very important conference for both academic and the industry. And so, for example, the top 500 list we mentioned, right, is also announced in this conference every year. And the HPL benchmark is also announced in this conference. So basically all the milestone, the important announcement, they are made in this conference as well. Okay? And so Of course, though, that's how we get MPI, and a couple of years later, we have MPI2 to include the MPI IO, API, etc. And then I didn't follow after that, but I think we should have the MPI3 now. And what's get added usually are, but usually what we need is MPI and MPI-IO. That's already quite sufficient for most of the cases. And the new interface usually included some other specific or optimized API. For example, as we will see that supposedly MPI can only launch a constant or a fixed number of processes. Now, you cannot change the parallelism or to add and remove processes during execution. However, in the new interface, the new MPI library, for a certain use case, because needed, so they added the API to allow you to increase or decrease the number of processes on the fly. But of course, usually that will reduce the performance, and you will complicate your parallel programming logic. So that's just some special case. Or we mentioned MPI is message passing programming model, right? But shared memory could be useful and convenient in some way, right? In some cases as well. So the new MPI API also include the API to create those shared memory. Okay. Of course, we don't teach that in this course, but if you dig into those API, you might find something like that. That's maybe it's different or extended over what we told. And of course, you can see those are some special cases. Okay. All right. So so basically, what we teach in the class should be quite sufficient. Okay. All right. So we start with this programming model. We talk about message passing programming model. So you should already know it's a model that based on message passing API, right? Like send and receive, like we will see later. Okay. And for MPI, we also code it as a single program, multiple data programming model. So very similar to what we told before about the single instruction, multiple data, right? Cindy is a classification for parallel computer, the hardware. But the similar concept can be applied for software to your program as well. So that is the SPMD. So what's SPMD means is that basically when you write your parallel program, you only write one piece of program, or this program you wrote will be executed on all the processes. Okay, and so basically it's a model that assuming all the processes are running exactly the same code. But of course, to allow them to do different things, right? Collectively. So each of the process, of course, they can use different data index to apply on different data element. So to explore the data parallelism for parallel programming. Okay. So when you write this kind of code, SPMD code, usually the way to allow the process to do different things is through the data parallelism, or you can use those bridge, right, to conditionally execute different code on each processes. Because we are talking about software, the program. So of course, now this programming model still allow you to let each process to do entirely different thing. But normally we don't want to make them too differently. So it's usually just use a branch. So some part of code, they are doing different thing, but most of the time they are doing the same thing. So we can have a clear right, easier manage the parallel programming pattern. Okay. So like your homework one, when you write the MPI, you will definitely feel that you will just add a branch to your code to write your the logic of your parallel program. Okay. All right. This is quite different from thread programming because I think most of you have some experience on that already. So to compare, thread programming is definitely not a single program multiple data programming model. Why? Because supposedly each thread is execute a function, and usually we give them different function pointer to allow them to do entirely different things, right? So that concept is completely different in contrast to SPMD. Okay. All right, and you can imagine why MPI is using this SPMD model is because MPI is supposed to run a much larger scale, over maybe thousands or tens of thousands processes. So you will certainly don't expect then each of them to do different thing, right? They should do exactly the same thing, so you can easier to manage it. Okay. All right. So MPI specifically, usually we code each processes as a task. Okay. So task imply a process in MPI programming, and a single job, right? An application you wrote by MPI is what we call a job. So a job will consist of multiple MPI tasks, and each of them will run exactly the same code as we mentioned, and just allow them to do different things through branch or data parallelism. Okay. So as I mentioned also, by default or traditionally, for MPI job, it doesn't allow you to dynamically create or delete the MPI tasks during runtime. So the parallelism of MPI job is fixed and given by when you run the when you launch the job. Okay, so it will be controlled by a parameter in your execution command. Okay, all right. So that's what MPI jobs looks like. Okay, and MPI, right? Besides programming, of course, you have this MPI library. So the library not only provide you the API to do the programming, it also provide the library code to initialize or manage, or even sometimes tracking your MPI job. So as you will see in your lab, when you try to run an MPI program, you probably just type a MPI run command on your local machine. But then you will actually create processes even across machine to launch those MPI tasks on remote machine automatically. So all those things are done by the MPI library as well. Okay. And for programming, as we will show you, those send receive API code, right? So of course, that's how the MPI provided for parallel programming. Okay, and most of those APIs we mentioned are for sending and receiving messages. Okay, so you can communicate the process across even machine based on the distributed memory architecture. Okay. All right, so that's a brief introduction on what's an MPI job and how it will get executed across machine and do the communication. So next we will talk about how to communicate, right? There are many API, but they basically follow either synchronous communication or asynchronous, or they are blocking code or non-blocking code. Okay, so so first of all, when we talk about communication method, we usually can classify them, or discuss them in a way that whether it's asynchronous or asynchronous, or blocking or non-blocking. Okay, and those two terms, they are actually sometimes are talking about the same thing but from different angle. Okay, so for synchronous and asynchronous, they are referring to the communication process, right? For example, synchronous communication means the sender side and the receiver side, they can do the communication simultaneously, right? While asynchronous means they are not doing the sending and receiving at the same time, or they are not communicated at the same time or immediately. Okay, so for example, if you're making a phone call, right? It's obviously should be a synchronous communication, right? Because you have to wait until the other person pick up the phone, and whatever you said, the other person should get that immediately, right? Just like right now we have the live streaming meeting, it's a synchronous communication. And asynchronous communication is like writing an email, right? So you click send, but you never know when the receivers receive it, right? So that's an asynchronous communication. Or for our lecture, we record it, so you might want to listen and attend the class right offline by listen to our recorded video. Then that's an asynchronous communication and learning, right? So obviously we know the difference between the two. And so why is it important? Because later on we will see that if use synchronous communication, usually is easier to understand the behavior of your program, right? Because when you call send and you get return from this sending function, you can assume the receiver already received it. So you can know the status of your the other process. So it can avoid some of the issues. On the other hand, asynchronous communication, it makes it more complicated because you don't know when this communication is completed or when the receiver received it. So you probably need some acknowledgement, other handshake process to ensure those things. However, asynchronous communication has the benefit to overlapping the computation time and the communication time. Okay, so usually if you use it right, use it properly, it can help you to optimize your program performance. And the main reason is synchronous communication requires synchronization, which is important, right? It's an overhead. So if you can complete your program with asynchronous communication, then you can reduce those synchronization overhead. And usually that means when you send out a message, after you send out a message, you don't need to wait the acknowledgement. You can continue to do your own computation. So your computation time can be overlapped with the synchronization or those communication wait time. So you can reduce the overall time. All right. And so that's synchronous and asynchronous. When we think about our algorithm, usually that's how we try to design our algorithm. Okay? But when we do the programming, on the other hand, do the implementation, we know we actually need to code those function code, right? So the blocking and non-blocking is respect to those function code. So obviously, the blocking code means the function code will not return until its function is completed, or its send and receive action is completed. So that's what we call a blocking code. On the other hand, non-blocking code, as you should know, that means you make the code, but you don't need to wait until the code to complete. You can continue to execute the next function code or statement. So that's a non-blocking code. So obviously, you can say there is a direct one-to-one mapping between synchronous communication and blocking code. Also for the asynchronous communication with the non-blocking code, right? But beside this one-to-one mapping, it's still possible you, for example, implement synchronous communication through non-blocking code. Of course, that usually you will prefer to use blocking code to implement synchronous communication, but it may not always the case, or at least from the programming aspect, it still allow you to implement a synchronized communication through either blocking or non-blocking code. It depends on how you implement it, right? Okay. And another thing to note is that when we use the term synchronous communication, usually it's not only try to do data transfer or message passing. We also sometimes also try to, the purpose is to synchronize, right? Synchronize the steps or the execution status of two processes. For example, we may call a barrier, right? An MPI barrier, as we will introduce next. This code has nothing to do to transfer a message or communication. Its only purpose is to synchronize between processes, so they can be blocked to reach a certain single state of their program or a same place. Okay, so we can make sure they reach the same state. Okay, so that's why we need those synchronization. We need synchronous communication. Okay, right. So synchronous communication usually have more meaning to it, right? Not just from the programming coding aspect. All right. So we briefly introduce, how this communication or function code can be implemented by the MPI library. Okay, so you have a little bit idea of how exactly those API is supported by the library, right? What really happened under the hood. Okay. So here, of course, we don't distinguish between synchronized and blocking because we're assuming, right, you use blocking for synchronous communication. So for synchronous or blocking communication, as you can imagine, the communication only occur when the sender and receiver reach their send and receive function code, right? And so what happened is when the sender call a send function, it will send a request to the receiver and then block by the code until the receiver call the receive function, which will return the acknowledgement to the sender. So they complete this handshake and they know they can send the message now. Okay, so that's why whoever called the send or receive earlier will be blocked, right? Until they receive and send this acknowledgement at the same time, and then start the synchronous communication. And for receiver, it's the same thing. So we don't repeat it again. In the example below, that's the case when sender send is called first, receive is called first, and then the send function is called. So in this case, still, whoever call the send or receive first will be blocked. Okay. And of course, because it's a synchronous communication, you could argue that the message passing action can happen immediately and directly between the sender and receiver. That means we can probably directly copy the memory from the sender side to the receiver side, without maybe buffer in between. Okay. But however, usually that's not the case. In fact, the MPI library usually send the message in the same, process the message in the same way for both synchronous and asynchronous communication through a message buffer. Okay, so the message buffer is necessary for asynchronous communication because, as we mentioned, non-blocking code means after you code the send, for example, and then you don't need to wait. You can directly move on to the next statement. So why is that? The reason is because the message already copied to the message buffer. So the send function can directly return immediately after the message is written to the buffer. Okay, and so the buffer is always there because it's managed by the MPI library. So that means you don't need to wait until the receiver side code receive in order to write the message to the buffer. Okay, so that's why after you code send, you can directly return from the code as long as you write it to the buffer. Okay, and of course, similarly for receiver, when you code receive, you will try to pull the message from the buffer. Okay, and even different from even further, different from the sender. When you pull the message, try to pull the message from the buffer. No matter you have the message written in the buffer or not, it will return immediately. So that means if receive code and the receive function is called before the send function is called, before the message arrive in the message buffer, the receive function still return immediately. And what happened is it will no affect to your user buffer. So basically, you don't receive the message at all, but the receive function still return immediately. So that's why, as we will introduce later, usually the non-blocking receive need to work with another other API, right, to ensure you actually complete this receiving action. Okay, but from the definition of the non-blocking receiving function itself, it doesn't care whether it received the function or not. All it does is try to copy the message from the buffer to the receiver side. Okay, all right. So because of the message buffer, we can decouple the sender and receiver so they can perform their function in a non-blocking way and complete the communication in an asynchronous way. Okay? And finally, noted that you may wonder, so where is the message buffer, right? It's maintained by the MPI library, but it's a buffer, so it's a memory space that needs to be exist somewhere, right? So actually, this buffer, usually can be at the sender side, or it could be in the receiver side, or it could be at both sides. It all depends on the MPI library, how it implemented. But no matter what, the buffer is a logic that must be exist, right, to enable this communication. And for the so for even for the synchronous communication we mentioned, right, your message usually still get written and read out from the buffer, but just the behavior of the function is different. So for blocking send, after you write the message to the message buffer, you still have to wait there until you receive a acknowledgement that the message is read out from the message buffer by the receiver. Then you can return. Okay. All right. So, but the sending and receiving process, actually, they are the same. They all through this message buffer. Okay. All right. Okay. So, any questions now? All right. If not, it's 4:12. But I think we can have a short break until 4:20. Okay, and then we can come back and start the second part and talking about the API. Okay, so let's have an early break now, and please come back at 4:20.